On October 29, 2018, Lion Air Flight 610 plunged into the Java Sea shortly after takeoff. Just 5 months later, on March 10, 2019, Ethiopian Airlines Flight 302 met a similar fate, crashing moments after leaving Addis Ababa. Two brand new Boeing 737 MAX aircraft, two nearly identical tragedies, and 346 lives lost. The world watched in horror, demanding answers. What could cause two advanced airliners, from one of the most reputable manufacturers, to fall from the sky with such chilling similarity? This question ignited a global crisis of confidence in aviation and launched an unprecedented investigation into a plane once hailed as the future. The immediate aftermath of the second crash was swift and decisive. As the eerie similarities between the Lion Air and Ethiopian Airlines incidents became undeniable, countries around the world began to ground the Boeing 737 MAX fleet. From Europe to China, Australia to Canada, the aircraft was deemed unsafe to fly. This extraordinary action, affecting hundreds of planes, sent shockwaves through the aviation industry. Boeing, a titan of aerospace engineering, faced an existential threat, and the flying public's trust was severely shaken. The grounding wasn't just a precaution, it was an admission of a profound, unsolved problem. For decades, Boeing was synonymous with reliability and innovation, crafting aircraft that defined air travel. Yet, the 737 MAX, their latest iteration of a legendary plane, was now at the center of a global safety investigation. The initial narrative was unclear, clouded by technical jargon and the emotional weight of two disasters. Was it pilot error? Mechanical failure? A design flaw? The initial answers from Boeing were slow, and at times, seemed to downplay the urgency. But as investigators painstakingly collected evidence from the crash sites, a clearer, more complex picture began to emerge, a story not just of a faulty component, but of a cascade of decisions that prioritized speed and cost over safety. To understand the 737 MAX, we must first look back at its lineage. The Boeing 737 series is arguably the most successful commercial aircraft in history. First introduced in 1967, it became the workhorse of airlines worldwide, known for its versatility, efficiency, and reliability. Over 50 years, the 737 underwent numerous upgrades, evolving through generations like the Classic and Next Generation (NG) models. Each iteration introduced new technologies, improved performance, and maintained its position as a market leader. This long, storied history established a formidable reputation for Boeing, built on trust and proven engineering excellence. In the early 2010s, Boeing faced a formidable challenge from its European rival, Airbus. Airbus introduced the A320neo, an updated version of its popular single-aisle jet, featuring new, highly fuel-efficient engines. This immediately offered airlines significant cost savings on fuel, a major operational expense. The A320neo became an instant hit, racking up thousands of orders and threatening Boeing's dominance in the crucial narrow-body market. Boeing needed a swift and competitive response, one that would match Airbus's efficiency gains without undergoing a prohibitively expensive and time-consuming full aircraft redesign. Boeing's strategic decision was clear: rather than designing an entirely new aircraft from scratch, a process that could take over a decade and cost upwards of $10 billion, they would update the existing 737 airframe. This approach, while faster and cheaper, came with inherent compromises. The goal was to integrate new, more powerful, and fuel-efficient engines into the proven 737 design. This updated model would become the 737 MAX. The pressure to deliver quickly and competitively was immense, shaping critical design choices that would later prove to be devastating. The new engines selected for the 737 MAX were larger and heavier than those on previous 737 models. This presented a significant engineering challenge. The 737's low-slung design meant there wasn't enough ground clearance to simply mount the larger engines in the same position. To overcome this, Boeing engineers had to place the engines further forward and slightly higher on the wing. While a clever solution to a physical constraint, this modification subtly altered the aircraft's aerodynamic characteristics, particularly at certain angles of attack. This seemingly minor change would become a critical piece of the unfolding disaster. The repositioned engines introduced an unintended aerodynamic consequence. Under certain flight conditions, especially at high angles of attack where the nose of the plane is pitched up significantly, the new engine placement could cause the nose to pitch up further. This was an undesirable characteristic, as an uncontrolled pitch-up could lead to a stall, or the wings lose lift, a dangerous scenario that pilots are trained to avoid. Boeing needed a system to counteract this new tendency and ensure the 737 MAX behaves similarly to previous 737 models, maintaining flight characteristics pilots were already familiar with. This is where the Maneuvering Characteristics Augmentation System, or MCAS, entered the design. MCAS was designed as a background software function, intended to enhance the aircraft's handling qualities and prevent an aerodynamic stall. Its sole purpose was to automatically push the nose down if it detected that the aircraft was approaching a stall condition, thereby mimicking the feel and behavior of older 737 models. This was crucial for certification and for pilots to transition seamlessly from previous 737 variants without extensive retraining. On paper, it seemed like an elegant solution, a safeguard designed to make the plane safer and more predictable. But the simplicity masked a critical vulnerability. The most catastrophic design flaw of MCAS lay in its reliance on a single angle of attack, AOA, sensor. The AOA sensor measures the angle between the wing and the oncoming air, crucial for determining if a stall is imminent. In the 737 MAX, MCAS used input from only one of the two AOA sensors on the aircraft. If this single sensor malfunctioned and sent erroneous data indicating an excessively high AOA even when the aircraft was flying normally, MCAS would activate incorrectly, believing the plane was about to stall. It would then repeatedly command the horizontal stabilizer to push the nose down, potentially overwhelming the pilot's ability to recover. Why would such a critical safety system depend on a single point of failure? In modern aircraft design, redundancy is paramount. Critical systems typically use multiple sensors, cross-checking their readings to ensure accuracy and reliability. If one sensor fails, the others can provide correct data, or the system can default to a safe mode. The decision to implement MCAS with a single AOA sensor input was a significant oversight, made more concerning by the fact that the system could command significant flight control changes without any cross-validation. This design choice amplified the risk of a sensor malfunction into a potential catastrophe. Another critical aspect of the MCAS design was its intended invisibility. Boeing presented MCAS as a minor background function, not a primary flight control system. This classification had significant implications for pilot training and regulatory oversight. By downplaying its role, Boeing avoided the need for extensive additional simulator training, a costly and time-consuming requirement that airlines might resist. This decision was driven by the desire for a seamless transition for pilots, a key selling point for the MAX. However, it meant pilots were largely unaware of a powerful, automated system that could take control of their aircraft. Crucially, Boeing initially did not explicitly mention MCAS in pilot manuals. This omission was deliberate, stemming from the philosophy that MCAS was transparent to the pilot and operated within the existing framework of known flight characteristics. Pilots transitioning to the 737 MAX were therefore unaware of this new, powerful system's existence, let alone its potential to command repetitive nose-down inputs. They were expected to handle any unexpected nose-down commands using existing runaway stabilizer checklists, which were designed for different scenarios and might not be adequate for the rapid, aggressive inputs MCAS could generate in a fault condition. The lack of disclosure about MCAS meant there was no specific simulator training for the system. Pilots received computer-based training that focused on the differences between the MAX and previous 737 models, but this training did not cover the specifics of MCAS or scenarios involving its malfunction. Boeing's justification was that the plane would feel like other 737s, making extensive training unnecessary. This approach saved airlines money and time, a significant competitive advantage. However, it left pilots unprepared for a situation where MCAS malfunctioned, transforming a safety feature into a deadly trap. On October 29, 2018, Lion Air Flight 610, a brand new 737 MAX 8, departed from Jakarta, Indonesia. Just minutes into its flight, the aircraft began to experience severe control issues. Pilots reported problems with airspeed and altitude indications, fighting to maintain control as the plane's nose repeatedly pitched down. Despite their desperate struggle, the aircraft ultimately plunged into the Java Sea, killing all 189 passengers and crew on board. The speed and unexpected nature of the crash stunned investigators and the aviation world, marking a tragic end for a flight that had just begun. In the immediate aftermath, the cause of the Lion Air crash was unclear. Initial reports focused on possible maintenance issues and pilot actions. However, data recovered from the flight recorders, specifically the Flight Data Recorder, FDR, and Cockpit Voice Recorder, CVR, began to tell a chilling story. It revealed a struggle in the cockpit, with the aircraft's nose being repeatedly commanded downward by an automated system, while the pilots attempted to counteract it by pulling the control column back and trimming the nose up. This persistent battle against the aircraft's own systems baffled investigators. Investigators quickly honed in on a critical piece of evidence, a faulty angle of attack (AOA) sensor on the Lion Air aircraft. This sensor had been replaced the day before the crash due to erroneous readings, but it was found to be faulty once again. During the doomed flight, this malfunctioning sensor transmitted incorrect data, showing an AOA significantly higher than the actual flight conditions. This false information triggered the MCAS system repeatedly, erroneously believing the aircraft was approaching a stall. With each activation, MCAS commanded the aircraft's nose down, initiating the fatal sequence of events. The Indonesian National Transportation Safety Committee's preliminary report on Lion Air Flight 610 confirmed MCAS's central role. The report detailed how the system, receiving erroneous data from the single faulty AOA sensor, repeatedly activated, pushing the aircraft's nose down. The pilots, unaware of MCAS's existence and without specific training to counter its aggressive inputs, found themselves in a desperate, losing battle against an automated system they couldn't fully comprehend or disable. The design that allowed MCAS to command repeated nose-down inputs based on a single faulty sensor was now clearly identified as a catastrophic flaw. Following the Lion Air crash, Boeing issued an operations manual bulletin alerting pilots to the potential for erroneous AOA sensor data and corresponding MCAS activation. This bulletin provided guidance on how to use existing runaway stabilizer procedures to counter unexpected nose-down commands. However, it still did not explicitly explain MCAS or its mechanics, maintaining the system's hidden status. While a step towards acknowledging the problem, it was widely criticized as insufficient. The information was complex, hard to digest under pressure, and didn't provide the in-depth understanding pilots needed to combat such an aggressive system. The urgency of the underlying issue was still not fully grasped. The FAA, after reviewing the Lion Air data and Boeing's bulletin, issued an Airworthiness Directive, AD, making Boeing's guidance mandatory. This AD aimed to ensure all 737 MAX pilots were aware of the procedures to follow if erroneous AOA sensor inputs led to uncommanded nose-down trim. While these actions were intended to mitigate the risk, they relied on pilots correctly identifying the specific malfunction and executing a complex recovery procedure under extreme stress. The underlying single point of failure within MCAS remained unaddressed, a ticking time bomb despite these procedural advisories. The world hoped these measures were enough. Despite the tragic loss of Lion Air Flight 610 and the subsequent investigations, Boeing largely maintained that the 737 MAX was safe. They emphasized that pilots were trained to handle runaway stabilizer conditions, implying that the existing procedures were sufficient, even for an MCAS malfunction. Public statements focused on the robustness of the 737 family and the exhaustive certification process. There was a strong desire to reassure airlines and the flying public, but also a reluctance to fully admit the depth of the design problem. This stance would soon be tragically undermined, as history was about to repeat itself with devastating precision. On March 10, 2019, just 4 months after the Lion Air disaster, another Boeing 737 MAX 8, Ethiopian Airlines Flight 302, took off from Addis Ababa. Like its predecessor, it too crashed minutes after departure, killing all 157 people on board. The world recoiled in disbelief. The similarities were horrifying: a new 737 MAX, taking off, experiencing flight control issues, and crashing shortly after. This was no longer an isolated incident, it was a clear pattern, demanding immediate and drastic action. The tragic repetition shattered any remaining assurances about the aircraft's safety. Investigators quickly secured the flight recorders from Ethiopian Airlines Flight 302. What they found was almost an exact echo of the Lion Air data. The aircraft's angle of attack sensor again provided erroneous information. MCAS activated, repeatedly forcing the nose of the plane down. The pilots, despite their training and experience, struggled heroically against the automated system. The pattern was undeniable, revealing the precise mechanism of the previous crash had recurred, tragically demonstrating the inadequacy of the interim measures. The world watched, horrified, as the details of a systemic failure became undeniable. The second crash ignited a global outcry and an unprecedented crisis of confidence. Countries, one by one, began to ground the Boeing 737 MAX. China was the first to act, followed quickly by the European Union, Australia, India, and eventually, the United States. The FAA, initially hesitant, bowed to overwhelming international pressure and public concern. The entire global fleet of 737 MAX aircraft was now grounded, an extraordinary measure signaling a deep-seated problem that went beyond simple maintenance issues or pilot error. Boeing's reputation, once unassailable, was in tatters. With both crashes definitively linked to MCAS and its flawed design, Boeing faced intense scrutiny. Engineers, regulators, and the public demanded to know how such a critical system, with a single point of failure, could have been certified. The narrative shifted from individual incidents to a fundamental examination of Boeing's design processes, safety culture, and its relationship with regulators. The stakes could not have been higher, not just for the company, but for the future of commercial aviation safety. The investigation became a deep dive into decades of aerospace engineering and regulatory practices. Multiple investigations, including those by the NTSB, the FAA, and international bodies, converged on the same root cause: the MCAS system, triggered by erroneous angle of attack sensor data, and the pilot's inability to counteract its powerful, repeated nose-down commands. The lack of information about MCAS in pilot manuals and the absence of specific simulator training were identified as critical contributing factors. It became clear that the crashes were not due to a singular error, but a complex interplay of design choices, procedural omissions, and a systemic failure to anticipate and mitigate the risks associated with the new system. The global grounding of the 737 MAX lasted for 20 months, an unprecedented period for a modern airliner. This extended grounding severely impacted airlines, which had invested heavily in the new aircraft, and caused immense financial strain for Boeing. More importantly, it allowed time for a comprehensive re-evaluation of the aircraft's systems, a redesign of MCAS, and an overhaul of training protocols. The world waited, watching as Boeing worked to regain trust, not just from regulators and airlines, but from the millions of passengers who had lost faith in the safety of their skies. Boeing embarked on a complete overhaul of the MCAS software. The new version addressed the critical flaws that led to the crashes. Firstly, MCAS would now receive input from both angle of attack sensors on the aircraft, eliminating the single point of failure. If these two sensors disagreed significantly, MCAS would be disarmed entirely. Secondly, MCAS would only activate once per event, preventing the repeated nose-down commands that overwhelmed pilots. And finally, MCAS would not be able to command more nose-down input than pilots could counteract with the control column, ensuring pilot authority always prevailed. These changes were fundamental, aimed at making MCAS a true safeguard, not a threat. The most crucial software update was mandating that MCAS receive input from both AOA sensors. This simple yet vital change introduced redundancy into the system. Instead of relying on a single data stream, MCAS could now cross-reference information. If one sensor provided faulty data, the system would immediately detect the discrepancy. This ensured that MCAS would only activate when both sensors agreed that a high angle of attack condition was genuine, vastly reducing the risk of false activation and preventing a repeat of the tragic chain of events witnessed in the Lion Air and Ethiopian Airlines crashes. It was a basic engineering principle, belatedly applied. Another key software fix limited MCAS to only activate once per event. The previous design allowed for repeated activations, creating a relentless battle for pilots struggling to regain control. The updated MCAS would now initiate a single nose-down command, and then reset. This change ensures that even if a sensor malfunction persists, the system will not continuously force the nose down, giving pilots valuable time and opportunity to identify the issue and apply the correct recovery procedures. It was about giving back control, rather than wresting it away, in a critical situation. Finally, the revised MCAS was designed so that its nose-down command could never be more powerful than what the pilots could counteract using the control column. This change explicitly ensured that pilot authority would always prevail. In the original design, MCAS could potentially generate forces that made it exceedingly difficult for pilots to pitch the nose up, even with full effort. The update guarantees that a pilot's input on the control column will always override or counteract MCAS, returning ultimate control to the human operators. This restoration of pilot primacy was a crucial step in rebuilding trust. Beyond the software fixes, a significant change was mandated for pilot training. Comprehensive simulator training for 737 MAX pilots was now required. Previously, pilots could transition to the MAX with minimal computer-based training. The new requirement meant pilots had to undergo specific simulator sessions that included scenarios where MCAS malfunctions. This hands-on training allowed pilots to experience the system's behavior, practice recovery procedures, and develop the muscle memory needed to effectively respond to an MCAS anomaly. This was a direct acknowledgement that the initial training was insufficient and contributed to the tragic outcomes. While the technical fixes for MCAS and the overhaul of pilot training were crucial, the investigations unearthed deeper, more systemic issues. The crashes brought to light concerns about Boeing's internal culture, particularly how production pressures and cost-cutting initiatives sometimes overshadowed safety considerations. Whistleblowers and internal documents revealed instances where engineers felt pressured to approve designs, and where transparency with regulators was lacking. This was not just about a software glitch, it was about the environment in which that software was developed and certified. Boeing's drive to compete with Airbus and get the 737 MAX to market quickly created a pressure cooker environment. There was immense commercial pressure to avoid a full aircraft redesign, which would have been far more expensive and time-consuming. This translated into design choices that sought to adapt an old airframe to new engines, leading to the need for systems like MCAS. The expedited timeline and the desire to minimize additional pilot training costs for airlines all contributed to a culture where efficiency and speed sometimes took precedence over thoroughly vetting novel, complex systems and their potential risks. Investigations also revealed a concerning lack of transparency within Boeing and in its communications with regulators. Key details about MCAS, including its reliance on a single AOA sensor and its potential for aggressive nose-down commands, were not fully disclosed to the FAA during the certification process. There were instances where Boeing reportedly downplayed the system's capabilities and implications. This omission of critical information hampered the FAA's ability to conduct a thorough independent review, ultimately contributing to the system being certified with its fatal flaw intact. Some critics argue that over the years, Boeing's internal engineering expertise became diluted, partially due to a shift towards a more financially driven corporate culture in mergers. The emphasis reportedly moved from deep engineering prowess to maximizing shareholder value. This shift, combined with significant layoffs in certain engineering departments, may have contributed to a diminished internal capacity for rigorous self-oversight, potentially allowing design flaws to persist through the development process. The focus on delivering quarterly results sometimes overshadowed the long-term commitment to safety and engineering excellence. The FAA, the agency responsible for certifying aircraft safety in the United States, also came under heavy criticism. A major concern was the FAA's practice of delegating a significant portion of its certification authority to Boeing employees. Under the Organization Designation Authorization (ODA) program, Boeing employees were authorized to act on behalf of the FAA for certain aspects of the certification process. While intended to streamline approvals, critics argued this created a conflict of interest and undermined independent oversight, allowing Boeing to essentially self-certify critical aspects of its own aircraft. The delegation of authority meant that the FAA's own engineers and safety experts did not always conduct thorough, independent reviews of complex systems like MCAS. They often relied on Boeing's submitted data and analyses, rather than performing their own in-depth evaluations. This lack of rigorous, arm's-length scrutiny allowed Boeing's initial downplaying of MCAS's significance to go largely unchallenged. Had independent FAA experts rigorously reviewed the system, particularly its single sensor input and its powerful capabilities, the critical flaws might have been identified before the aircraft ever flew commercially. Another factor contributing to the FAA's oversight issues was a perceived lack of resources and staffing. Over the years, the agency's budget and personnel numbers had not always kept pace with the increasing complexity and volume of aircraft certification work. This meant that the FAA was often stretched thin, further necessitating the reliance on manufacturer delegation programs like ODA. The systemic issues were not just about policy, but also about the practical limitations faced by a regulatory body tasked with ensuring the safety of an ever-growing and technologically advanced aviation industry. The 737 MAX crisis fundamentally reshaped the landscape of aviation regulation. The FAA and other international regulators have since committed to more stringent, independent oversight of aircraft certification. There is a renewed emphasis on thorough, transparent reviews of new and modified systems, with less reliance on manufacturer self-certification. The global aviation community recognized that the existing framework had failed, and a stronger, more independent approach was essential to prevent future tragedies. This painful lesson spurred a re-evaluation of how safety is ensured in the skies. The real reason behind the Boeing 737 MAX crashes was not a single, isolated fault, but a tragic confluence of factors. It began with the commercial pressures on Boeing to quickly compete with Airbus, leading to the adaptation of an older airframe with new, larger engines. This necessitated MCAS, a powerful automated system. Its critical design flaw, reliance on a single AOA sensor, combined with Boeing's decision to downplay its significance, omitting it from manuals and pilot training. This created a scenario where pilots were completely unprepared to handle a malfunction, leading to the devastating loss of 2 aircraft and 346 lives. Beyond the technical and training failures, the crashes exposed profound systemic issues. A corporate culture at Boeing that prioritized production and cost-cutting over uncompromising safety. A regulatory system, particularly the FAA, that delegated too much authority and lacked the resources for truly independent oversight. These systemic weaknesses allowed the technical flaws to propagate, remain undetected, and ultimately lead to catastrophe. The incidents were a stark reminder that aerospace safety is not merely about engineering brilliance, but also about robust corporate governance and unwavering regulatory vigilance. The 737 MAX crisis represents one of the most painful and significant lessons in modern aviation history. It underscored the critical importance of transparent design, comprehensive risk assessment, and effective communication between manufacturers, regulators, and pilots. The industry learned that even minor aerodynamic changes can have profound consequences if not thoroughly understood and communicated. It reaffirmed that automated systems, while enhancing safety, must be designed with ultimate pilot authority and robust redundancy, and that pilots must be fully trained on every aspect of their aircraft, especially the hidden ones. Boeing has since initiated comprehensive reforms, overhauling its engineering division, improving safety processes, and working to restore trust with both regulators and the public. The 737 MAX has returned to service in most parts of the world, with its updated software and mandatory pilot training. While the scars of the crashes remain, the industry is committed to ensuring such a tragedy never happens again. The path to rebuilding trust is long and arduous, but the commitment to safety, reinforced by the painful lessons of the 737 MAX, guides the future of air travel. The legacy of the 737 MAX crashes will continue to influence aerospace engineering, regulatory practices, and pilot training for decades to come. It serves as a permanent reminder that in the complex world of aviation, no single factor operates in isolation. Safety is a holistic endeavor, demanding relentless vigilance from designers, manufacturers, regulators, and operators. The 346 lives lost were a devastating cost, but their memory has forged a renewed commitment to ensuring that the skies remain the safest place to travel, a testament to humanity's ongoing pursuit of safer flight. Aviation safety is not a static achievement but a constant evolution. Every accident, every incident, provides invaluable data that helps engineers and regulators improve future designs and procedures. The 737 MAX crashes, despite their horrific nature, have initiated a profound re-evaluation of how aircraft are developed and certified. This commitment to continuous improvement, driven by a deep understanding of past failures, is fundamental to the industry's ability to maintain its exceptional safety record. The journey towards perfectly safe skies is unending, fueled by lessons learned at immense cost. Modern aircraft are extraordinarily complex machines, integrating thousands of mechanical, electrical, and software systems. The 737 MAX crisis highlighted that as aircraft become more automated and software-driven, the interface between human pilots and these sophisticated systems becomes paramount. It's no longer just about preventing mechanical failures, but about ensuring that software algorithms, especially those that can override pilot input, are impeccably designed, thoroughly tested, and fully understood by those who fly them. The human-machine interaction is now a central pillar of aviation safety, requiring meticulous attention. The intense competition between aerospace giants like Boeing and Airbus is a driving force for innovation, but the 737 MAX tragedy serves as a cautionary tale. The pressure to deliver new, fuel-efficient aircraft rapidly can inadvertently lead to shortcuts or compromises in the name of speed and cost-effectiveness. This incident forces a re-examination of how commercial imperatives are balanced with uncompromised safety. The industry must ensure that competitive pressures never erode the fundamental commitment to rigorous design, exhaustive testing, and transparent regulatory engagement. Profits cannot come at the expense of lives. The FAA's certification process, specifically the ODA program, underwent significant review and reform post-MAX crashes. While delegation to manufacturers can expedite processes, the balance of independent oversight and industry partnership is crucial. Reforms aim to enhance direct FAA involvement, increase transparency in the certification of critical systems, and ensure that the agency has sufficient resources and technical expertise to conduct its own thorough evaluations. The goal is to rebuild a robust regulatory framework where public trust is paramount and where independent scrutiny is never compromised for the sake of efficiency. The incident highlighted the increasingly critical role of software in modern aircraft. MCAS was entirely a software-driven system, designed to compensate for a hardware change. This underscores the need for software engineering in aviation to be held to the highest possible standards, with extensive testing, verification, and validation processes. Bugs or design flaws in code, even in what appear to be auxiliary systems, can have devastating real-world consequences. Software is no longer just a component, it is an integral, life-critical part of the aircraft's very being, demanding unparalleled rigor. Pilots place immense trust in the automated systems that assist them in flight. The 737 MAX crashes eroded this trust, as pilots found themselves battling a system they didn't know existed. This incident emphasized the importance of ensuring pilots fully understand the capabilities and limitations of all automated systems, especially those that can intervene in fundamental flight controls. Trust is built on transparency and comprehensive training. Without it, automation, intended to be an aid, can become an adversary. Restoring this trust is paramount for the future of aviation, as automation continues to advance. While the headlines focused on Boeing and the FAA, the ripple effects of the 737 MAX crisis extended throughout the entire aviation ecosystem. Airlines faced financial losses and logistical nightmares. Passengers felt fear and uncertainty. The families of the victims endured unimaginable grief and tirelessly advocated for justice and change. The crisis touched every part of the industry, forcing a collective introspection and a renewed commitment to the principles of safety that underpin all air travel. This was a shared tragedy, and the lessons learned belong to everyone who works to make the skies safe. As the aviation industry moves forward, the shadow of the 737 MAX crashes will serve as a constant reminder. Future aircraft designs, software implementations, regulatory approvals, and pilot training will all be scrutinized through the lens of this painful experience. The hope is that this tragedy, while devastating, will ultimately lead to an even safer era of air travel, characterized by greater transparency, stronger oversight, and an unwavering commitment to putting safety above all else. The journey of flight has always been one of learning, and this chapter has added profound, indelible lessons to its history.